Is my screen visible?
Yes, sir.
So we left off with the hands-on session on HFSS. So the example that we are going to take is the example that we have seen during the presentation. One such example was this, wherein on top side we are having a normal patch antenna. On the bottom side we are having a slot. This is the slot that we have. This is the slot that we have, and then we are having 5 diodes here: diode 1, diode 2, diode 3, 4, and 5. Now, depending on the resonant frequency that you are looking for, you can place these diodes at your required distance, right? So, whatever has been presented in this paper, the authors have designed the slot to get resonant frequencies varying from 2.1 gigahertz to about 3.6 gigahertz. So accordingly, they have chosen the placement of these diodes at certain distances which are given here. Okay, so basically what we are trying to do is we'll be designing a microstrip patch antenna, then followed by etching out a slot in the ground plane. And once we etch out the slot in the ground plane, then we will be making the provision for keeping the diodes. And after that, because we need to bias the diodes, we need to operate them independently. So as discussed in our earlier class, if you are not separating the ground plane using these slots, then we will not be able to bias the diodes. So we need to have 2 separate lines for biasing the diode. So top side we will be applying the positive voltage, bottom side we will be applying the negative voltage or the common potential or ground potential, right? So these horizontal slots that we are having here, they are used for segregating the positive plane of the supply with the negative plane of the supply. And then we are having 2 more slots here on the right side and 2 more slots on the left side. These are used for separating the biases for the 5 diodes, right? And once that is done, basically we are using a capacitor. If you see, let me make this. So if you are seeing here, you are seeing blue rectangles on the slotted lines. So these rectangles, blue rectangles, are the capacitors, right? We need to put these capacitors so that they act as short circuit for RF signals. So there is no leakage of the RF signal through these slots, and the radiation is happening only through the field that is excited in these slots. If you are not putting these capacitors, then the leakage happens through these slots as well. So RF signal will leak through these slots, resulting in degraded performance of the antenna, right? So now let us start off with the hands-on session. So coming to the substrate that we are taking RF 35 substrate. Then thickness of the substrate is 3.04 mm, and permittivity of this substrate is 3.5, right? And the total length of the substrate dimensions are we are taking 60 mm by 60 mm, right? So this dimension is 60 mm by 60 mm. The patch dimension is patch dimension is 18.3 mm. This is 18.3 mm, and this width is 29 mm, right? And the feed line consisting of your CPW line and your microstrip line. This microstrip line is having dimension length of 13 mm and width of 11 mm, right? So let me just put this up. So B is 13 mm, line width is 11 mm, and the CPW line where we are cutting off 2 slots to make it has 50 ohm. We are taking the A dimension as 6.4. At this offset distance, you are having 50 ohm, and then the gap width is taken as 1.5 mm. So the slot that we are cutting here is having a width of 1.5 mm, resulting in 50 ohm line here, 50 ohm microstrip line, and the position at which we are feeding the signal is also 50. So we should be getting good return loss for this particular patch antenna. So first thing that we do is uh, we open HFSS, then we right click and say insert HFSS design, right? Once we are inserting HFSS design, we get our schematic where we are going to draw the patch antenna, right? So first thing that we will be doing is we'll be changing this solution type to model. Generally, when we are opening HFSS, if you are not setting the properties, then it opens as network analysis and terminal. Terminal we generally use it for circuit-based passive simulations, and for your antenna we generally use model, right? And then we select model here and say OK, and then we save this design. So when we are saving this design, we name this as your reconfigurable patch, right? And then save it. After saving this, here we'll rename this as your microstrip patch underscore reconfigurable, right? So we rename this HFSS design as microstrip patch reconfigurable, and then we will first make the ground plane. So for making the ground plane, we'll select a rectangular box here. So we'll select the box, draw a random box. We draw a random box, then we double click on box 1, then say ground plane, right? And we give the material properties as copper, and say OK. Now we need to define the dimensions. So according to this, we have considered this as ground plane, which is having same dimensions as the substrate. So the dimension should be 60 mm by 60 mm, and thickness would be 35 micron. So we'll double click on create box. So here we are putting this as sub x divided by 2, sub y divided by 2, and height, let us put it at 0 itself. And then we'll give these dimensions as 60 mm, and sub y also has 60 mm, right? Now x size we are putting it as sub x, and y size we are putting it as sub y, and the thickness of copper is, let us put it as t. So this T is 0.035 mm, which is 35 micron. Typically, whenever you are selecting a substrate, the copper thickness sometimes the manufacturer gives 17 micron or 35 micron, and if you require coppers with other thicknesses, we need to mention it to the manufacturer or the vendor who is supplying the substrate to provide us copper with certain thickness. So the typical thicknesses that we have is 17 micron and 35 micron. So here we are considering the thickness of copper has 35 micron. And then say we apply it, and then so now we have defined the ground plane, which is of dimensions. X-axis is 60, y-axis is 60, and z dimension is thickness of copper. Right? Now, let me define the ground substrate. For substrate, I'll select this, right click, edit, copy, and then I'll right click here, edit, paste. Right? And then I'll rename this as substrate. I'll rename this as substrate, and then I'll edit the material. I'll type RF35. Right? So or else I'll type RF. So this is a tectonic substrate with dielectric constant as 3.5 and the dielectric loss tangent as 0.0018. Right? So this is already defined. In case the substrate material is not defined, you can edit or add that material using this option, add material, wherein if you are adding, you can define the relative permittivity, permeability, conductivity, and dielectric loss tangent, magnetic loss tangent, magnetic saturation, land G factor, delta H, and so on. Whenever we are defining dielectrics, we generally define relative permittivity, then bulk conductivity for the metal that we are using. Here we are using copper, so it would be 5.8 e power 7, and then dielectric loss tangent. And the other things, relative permeability, magnetic loss tangent, magnetic saturation, delta H, these things come when you are defining ferrites. So because we are not defining any ferrites, we are defining only dielectric. So we have to define relative permittivity, bulk conductivity, and dielectric loss tangent. Right? So the material that we are using is tectonic RF35. So we have selected that material and we'll say OK. And then say OK. So now we have a substrate, but then if you are seeing, it is overlaying with the ground plane. So we need to have the ground substrate over the ground plane. So we'll start this Z at T, which was the highest point of your ground plane, and then thickness of the substrate, let us put it as H, and this is H is 3.04 mm, right? So we'll say OK. Here we'll define H as 3.04, right? And then say OK, apply. So now if you see here, we have the ground plane, which is shown in which is highlighted in pink, and the substrate, which is highlighted once again in pink. So there is no overlapping of your copper and substrate. So you are having your ground plane, then substrate. On top of this, we need to have the patch. So we need to define the patch here. So now we have defined ground plane. We need to now define the patch. So if you are seeing, the patch length is 18.3 mm, width is 29. So I am keeping the length along y-axis and width along x-axis. So once again, I'll take I'll draw a box, or else I can do copy paste and do it. Here I'm taking a box. I'm defining this box, and then I'll rename this by double clicking on box 1 as patch. And the material that I'm using is copper. So I'll select copper and say OK. And now I need to define the dimensions. So along x-axis, I'm putting the width. So I'll call this as patch W divided by 2. And along y-axis, I'm considering the length of the patch. So patch L divided by 2. And this is at a height starting with ground plane. It starts at 0. Thickness of copper is T. So I'll put T. Plus over that, we are having the substrate whose height is H. So I have put H. Right? And patch width is 29 mm. Right? And then patch length is 18.3 mm. Right? And then below X size, I'll put it as patch W. And then y-axis, y size has patch length L. And then thickness of copper is T once again. Right? So now I have defined my patch. So I have got my patch. Next thing that I need to do is define this feed line, right? I need to define this feed line. So once again, I'll take a box, I'll draw a random box, and then name this as feed line. And material is copper. So I'll select copper, say OK. Now I need to define the dimensions. So along y-axis, I am coming towards negative y at a distance of minus patch L divided by 2. And width of this is, I'll say this feed W divided by 2. And my starting position is minus pat L divided by 2. And thickness of my substrate is, or the thickness at which I need to place it is T plus H plus T. Sorry, T plus H, right? So now I've got my X size as PW. What is the width of the feed line? Width of the feed line is 11 mm. So I'll put here 11 mm. And then here I'll write this as feed W. Then this one will be, I've started, I need to bring this line length till this point. So this is pat L by 2, this is sub y by 2. So I'll subtract both the distances. I'll say minus sub y divided by 2 minus pat L divided by 2, right? And then thickness is, I'll say okay. So I have got my feed line for this particular patch. So I have made the patch feed line. Now I need to make this cutout, right? So for a cutout, let me select one more box. I draw this box and then say rename this as cutoff. I'll put the material as vacuum because anyway I'm cutting it off. And then here I'll define. Now if you are seeing this, if you are seeing here, this is my center position. Half is up, half is bottom. So I'm at minus pat L divided by 2. And if I'm looking along my X, this is my feed W divided by 2. So I need to move a distance of the slot width, and from pat L divided minus pat L divided by 2, I need to move in the forward direction, positive Y direction, a distance A. So accordingly, I'm making the slot here. Here I'll put it as feed W divided by 2. And then this is at minus pat L divided by 2 and at a height of T plus H, right? And now I need to move a distance of 1.5 mm. So this is feed gap, and I need to move in the negative direction. So I'll put minus feed gap, and this feed gap is 1.5 mm. And then I need to move in the positive direction by a distance of A. So I'm putting the variable A and giving this as 6.4 mm. And thickness of copper is T. So now I have my slot cut out, my slot here. I need to make one more slot here. One way of doing is copy this, paste it, and change the dimensions here. This has positive feed W divided by 2, and this is positive gap. That is one way of doing it. The other way of doing it is select your cutoff, then go to edit, right click, go to edit, then say duplicate mirror. And once you click mirror, click on tab 0, tab 0, tab 0, and then say enter, right? And then you give dx as 0.1, and you will get your duplicated cutoff here. So you are seeing two cutoffs here, symmetric along your x-axis. So if you are seeing here, when I have duplicated, I have given, sorry, when I have duplicated here, I'm duplicating it along the axis at which I want the duplicated cutoff to be present. So it's along x-axis, so I have put here 1, okay, or 0.1. And after that, I'll be selecting my patch and I'll press control and then select cutoff 1 underscore 1, and then I'll say subtract. So I'll go to modular boolean and then I'll say subtract. So whenever we are subtracting, these are the parts that will be subtracted from this patch. So whichever part you want to remain, you will put it on the left side. Whichever parts you want to be removed, you will put it on the right side, right? And then say OK. So now we have made the patch as we want here, right? Any queries till this point?
No, sir. Proceed, sir.
Right. So now we have made the patch. Second thing that we need to do is we need to make the slots. So before making the slots, I'll make the airbox, right? So for airbox, I'll select any one ground plane or substrate, say copy, and then paste it. So now I rename this as airbox, and then I'll put this as vacuum, say okay, right, and then I'll say this as 3 times sub x. I'm starting at sub y, and then I'll move in the other direction. So this is into 3 into 3, right? And height, I'll put this as minus 10 times h, and here I'll put it as 21 times. Let us see what we got. So we have got airbox wherein one side we are aligning it with the patch, other side I've made it a bigger box, and then I have taken the x dimension and y dimensions as 3 times the substrate width. I did not make this airbox symmetric with the purpose that I'll be defining a wave port at this point. Instead of defining a lumped port, I'll define a wave port. The reason we'll be seeing later. So I've defined my airbox, and now I'll right click on the airbox and then assign the boundary as radiation boundary. Right? I've assigned this boundary as radiation boundary. So I'll be getting a radiation boundary here. Right? And then now let us draw the bottom part. So now in the bottom part, first thing that I'll be doing is I will be drawing a slot, then so I'll be dividing this into few parts, wherein first I'll draw a slot, right? Then I'll make provision for my diodes like this, where I'll be soldering the diodes. So I'll make these provisions here like this on either side. Right? So I'll have my then what I'll do is I'll make a slot here for the bias, then a slot here for the second bias, and third slot here. And I'll mirror this here, right? So that I get the different biases for my diodes. So this is what I'll be doing now, and then we'll be having our diodes placed here. We'll have the diodes placed here, right? And we have a capacitor which we will be placing here, right? Accordingly, at these positions we'll have capacitor. This position we have capacitor. This position we have capacitor. This position capacitor, and this position capacitor, right? This position, this position, this position, this, and this we have diodes. So total we are having 5 pin diodes and 6 capacitors placed, right? This is what we'll be doing right now. So if you see from the edge of the patch, the slot is at an offset distance of G, right? And the dimension of G is 15.38. So let us first make the slot. I'll take a rectangle. I'll draw a random rectangle. Then I'll rename this as slot, ground slot. And see, okay. Here, my slot position will be, I need to move at an offset distance of G from the edge of the patch, right? And then along this dimension, my width or the slot length is 36 mm. So I'll say slot L divided by 2, and I'm starting at minus pad L divided by 2 and moving the distance away G, right? Then minus slot width divided by 2, right? And this is at a distance of 0, right? Because my thickness of the slot is at 0. Then the slot length is 36 mm, width gap, sorry, G is 15.38 mm, and then slot width is 2 mm, right? And once again I'll write slot L here, then this is slot W, and then thickness is T, right? So I'll apply. So I've got a slot here on the ground plane. So if I remove the patch, I'll hide this. So I have my ground plane, and then over that I have made this slot, right? So next thing that I'll do is I'll subtract this slot here. I'll select ground plane, I'll select ground slot, then I'll say modular Boolean subtract. So my ground plane is on the left side. The part that I need to make a slot is on the right side. Then I'm cutting a slot. So I have got my slot. So whatever I've done, I've first made this slot. Now, after making this slot, I'll make this small feed points for my diode. Right? So I'll take a rectangle. I'll draw a rectangle. Then I'll say the pad. Right? I'll say this as diode pad, and then this diode pad is having pad W divided by 2, or let me put this as diode pad divided by 2, and this is at a length of minus pad L divided by 2 plus G minus or plus G plus slot W divided by 2, and at a thickness of position is 0, and then pad width is 0.3 mm. And here X size, I'll put this as D pad, and here the pad length is also 0.3, and thickness is D. Okay, so I'm having a diode pad here. Okay, so I've got my diode pad here. Let me make this diode pad length as say 2.3. I've put the diode pad length as 0.8 mm, right? So once I have done this, the material that I need to assign here is copper. I'll assign this as copper, and then I'll make a copy of this. Edit, copy, edit, paste, right? So now here I'll put this as minus, and I need to go on the positive side. I'll put this as, I'll remove this minus here. Apply. Okay. So now I have made the next part that is required for me, this part. So I have made the diode pads. Next thing that I need to do is I need to have my diode pads here, 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 and here. What I'll do is I'll rename this diode pad V1 pad. Okay, and this I'll make this as given pad 1, or let me put this as given pad bottom, and this is given pad. Okay, so I'll edit, copy, I'll paste them, right? And then what I'll do is I'll rename them. This is D2 pad bottom, and this is D2 pad top. Okay, now what I'll do is I'll select both bottom and top of D2 pad, right click, edit, arrange, move. And then I need to move a distance away from this. So 0, 0, 0, 0. I'll put all zeros. Then dx also I'll put 0. So then what I'll do is I'll open this. I need to move a distance of, so from center this distance is C. So I'll be moving a distance C on the positive side, and this C is 13.95 mm. I'll say apply. Okay, so I've moved this point here. Same thing I'll do here. I'll say, so I've got my second diode pad here, and then I'll copy paste this once again. Edit, copy, edit, paste. So here I'll rename this as 3, and then here my second position of the diode is at D, right? So this I'll put this as D. D is how much? 16. And this is once again right. So now I have made my diode pads here. What I'll do is I'll copy all this. I'll select all from D2 to D3. I'll say edit, copy, edit, paste. One way of doing it is I'll select this and then I'll mirror them onto this side. Instead of doing that, what I'll do is I'll make this as this is 4. Fine. So I need to move them onto this side symmetrically. So I'll just put a negative sign here. So we have made all the diodes now. So we have all the diodes, and simultaneously I make this rectangular sheet here for defining this diode. So let me take that. So I'll first draw a rectangle here, right? And this rectangle I'll say diode 1. I'll say okay. And here the position of this I'll take it from here. And then here I'll put it as D and W, and length is slot W divided by slot W minus 2 into D pad L, right? And say apply. So this has to move on the positive direction. Where did it go? I'm at negative point on the positive side. Sometimes what happened? Add L divided by 2 G. I'm at the center. Okay. Center. I'm at the center. Then minus L divided by 2. This is I'm at this position. Just a minute. So pad L minus G divided by 2 plus d pad L divided by 2, and this would be d pad L. What is happening? I made some mistakes on there. So this is d pad L have moved here. So I have put my diode pad here. What I've done is I've taken the dimensions here and then I've added d pad L to this dimension, and whatever gap is there, that gap I've put here, right? So accordingly, this will be slot W divided by 2, slot W minus 2 into d pad L, right? So this is what we'll be having. And once again, after I have defined this diode 1, I'll say edit, copy, edit, paste, and then I'll say I'll move this, edit, arrange, move. Once again, I'll say tab 0, 0, 0, and then once again 0. I'll press enter. Here I'll put this as C. Say OK. So now I've got my diode here. Similarly, I'll do it for the others. Edit, copy, edit, paste, and here I'll put this as, and I'll copy these two, minus, right? So we have got all the diodes along with the diode pads. Next thing that we need to do is make the slots here, right? So for making the slots, I'll draw a sheet here or a box here, and then this box is at a distance slot L divided by 2, and this is at a position minus pad L divided by 2 plus G plus slot W divided by 2, and thickness is 0. And then I need to move to the right, so sub x divided by 2 minus slot L divided by 2, and then I need to move up. I'll put this gap as 0.2 mm, and then thickness is T, right? So I'll apply. So I got a slot here. So I've got my slot here. I got this slot. I'll also make these slots here. I'll say this slot 1. And then what I'll do is I'll edit, copy and paste my slot. Then I'll move this up by say 2 mm. Okay. Here I'm not much concerned about what is this distance. That distance should be enough for me to solder my wire here, right? So I put, let me put this as 5 mm, right? So I have put this and I need to move to this point. So this point is D and this is C. So I need to be somewhere between that. So D is 16. Let me consider this C has 14. I can have this length as around 15 mm. So from here, from center, it should be 15 mm, right? So I'll say sub x divided by 2 minus 15 mm. Where did I make a mistake? Sorry. So I'm at this distance at the center. I'll copy this. Paste it. So I'm at this distance and I'll make this as 0.2 mm and this length as minus 5 mm, right? So I've made this slot. So what I'll do is I'll copy these two, edit, copy, edit, paste. So I'll make this as 10 mm, this as 18 mm, see apply, sorry, right? And then this is 10, I'll make this minus 10, right? So now I have my ground plane, I have made the slots. What I require now is I need to have a rectangular sheet here, here and here, right? So I'll take a rectangular sheet, I'll draw some random rectangle here and this rectangle, I'll say this has capacitor, okay? And then this capacitor, I'm having it as at slot W divided by 2 and this is at a height minus at L divided by 2 plus G plus slot W divided by 2 and it is on P, no, it's on 0 and then it's coming down by 0.2 and width 0.2, this is also 0.2. Okay. HFSS properties slot L divided by 2. Sorry, this has to be slot L divided by 2. So I have my capacitor here. I need to move in the negative direction. Y size is negative. So I have made my capacitor here. I need to make one more capacitor here. So, and for this capacitor, I choose slot 3. This I'll remove, and then Y is on the apply. Okay. And similarly, I'll draw one rectangular sheet here, and from this I'll copy the position and define it here. Right? I'll remove this. 1, 2, this 1, 2. Okay. So now I have my capacitors as well. I'll rename this. This is capacitor 2. And this is capacitor 3. So I have my slot lines on one side along with the capacitors. So what I'll do is I'll select these slot lines, right click, edit, and I'll say duplicate mirror. Then I'll say tab 0, tab 0, tab 0, enter, and I want it along the x-axis, so I'll put 0.1 here and then say enter. So I got my slot lines onto the other side. Similarly, I'll make my capacitors here, edit, duplicate, mirror, then I'll say tab 0, 0, tab 0, enter, and then tab my 0.1, enter. So I'll get my capacitors here. Sorry, I forgot capacitor. Edit, duplicate, mirror, tab 0, tab 0, tab 0, enter. Point. So now I have my capacitors as well. Now what I'll do is I'll take my ground plane and then subtract all these slots. And then say modular Boolean subtract. Right? So I got my required structure, whatever I'm having here. Now I need to define my diodes here. So as we discussed earlier, first let me define the capacitors. So the capacitor values I'm taking it as 100 picofarad. So I'll select capacitors, right click, assign boundary, and here I'll say lump RLC. So as we discussed, we are having serial and parallel. So it doesn't matter when you are having one component, you can either choose serial or parallel, right? So I'll say capacitor, and this is 100 picofarads, right? And when I'm defining this line, I'm making sure that all the capacitors are moving in the same direction. So I'll click on the top and the arrow is pointing downwards. I have defined this. Next, I'll be defining this capacitor. So capacitor 2, right click, assign boundary, RLC, then I'll say capacitor, value is 100 puff, and then new line I'll define from my left to right. Say OK. Then my capacitor 3, assign boundary, RLC, I'll say capacitance value is 100 puff, and I'll define this here like this. Right? So I have defined my capacitors on the right side. I'll define the capacitance on the left side. So here I'll say right click, excitation, lumped element, sorry, boundary, lumped RLC, capacitor, value is 100 puff, new line, and then from top to bottom, I am defining the line. I'll define the lines as I have defined such that all the orientations are in the same direction. Lambda RLC, 100 puff. So this arrow will be now from my right to left. Sorry. Capacitor 2 is this. And then my capacitor 3. Boundary RLC 100 puff. Right. So now I have defined my capacitors. Now coming to my diodes. So as we discussed in our earlier lecture, whenever we are having this diode, so let me just open this. We need to have AR50-02, right? So we have the data sheet for this. The inductance is depending on which diode you are choosing and package that you are choosing. You can have the inductance like this, or you download the SPICE model, and from there you will get your package parasitics, wherein you can define the diode. Right? Either you can use this, or you can go back to your diode. This they are not doing. Description. I think they have done this. So we have the SPICE model. We'll download here, and we can directly use the SPICE model from here, right? So this was what we have seen in the earlier case. We are having inductance at the two sides, anode as well as cathode, parasitic capacitance, then inductance here, and your chip. So you can have this chip as either your capacitance or resistance, right? So now one way of using it where you are using at higher frequencies, then you may have to follow this model, or else you can simplify this model by combining this inductances. Because they are falling in series, you can add them up and then represent it with a single inductance, right? And then you are having inductance and resistance in parallel with a capacitor, right? So accordingly, we can simplify this network to have a equivalent circuit. So when you are working at lower frequencies, you need not worry about these parasitics. Like if you are working anything around say few megahertz or hundreds of megahertz, maybe you are not much worrying about these capacitances. But if you are working at higher frequencies, say around 5 gigahertz or 6 gigahertz, then these capacitances and inductances are going to affect the performance of your diode, right? So here we are having two things. One is your parasitics. You want to be accurate, then you need to consider all these parasitics. But at lower frequencies, it may not be required for you, because it will not affect the simulation results. So basically we are having RS as 0.42, on resistance as 0.42, and the total capacitance that you are having for the diode which is coming from the data sheet, is the total capacitance for the diode operating around 1 to or greater than 1.1 gigahertz is 0.15, and which is 150 femtofarads, and the package capacitance that you are having is 90 femtofarads. So your CJ0 for the diode is 60 femtofarads, right? So it is 0.06 picofarads. That is the junction capacitance CJ0 for this diode, and the resistance that you are having, intrinsic resistance that you have for the diode is 0.42, right? So whatever we are having here, 0.42 is the resistance. So what we can have here is that you are having you have an inductor, then here you are having your capacitor, then you are having an inductor here followed by resistor or a capacitor here, and then that is connected to your L here, right? So we can simplify this by combining these two into a single inductance, and then LR or LC circuit, whatever you are having, you can convert this series LC, whatever you are having here, it can be easily converted to a parallel LC, right? We have fixed formulas for converting this into series into parallel. So once you are converting this, let me assume that this is in off condition. So you are having L and C. You can convert this LC network, series LC network, to parallel LC. And now what you have is these two inductances. You are having L, then followed by you have a C, then you have a C, and then you have a L, right? This is what you are having. So you can add these two capacitances because they are in parallel. Effectively, you are having an L, and then you have a C, and you have a L, right? So this is the equivalent circuit that you have in off condition. You are having it in off condition, right? Now you can define this here. Instead of taking one sheet, you can have two sheets. For one sheet you define L, for the other sheet you take this parallel, whatever I have defined here for the capacitor. So if you are seeing here boundary condition, I have series and parallel. So here for this I'll use parallel case, and for this I'll have parallel or series. So I need to define two sheets here if I have to include the complete model of the diode with inductance, with the parasitics. So let me do one thing, I'll show with that. Okay, so in that case, if I want to have this in two parts, what I'll do is I'll divide by size white, right? And then I'll say edit, copy, edit, paste, and then I'm showing it for only one diode. It can be done for others as well. So in off condition, I'm having L. So what I'll do is here I'll consider this as excitation RLC, and here I'll put this as inductance, and the total inductance that I'm getting here from the parasitic model is LAO, which is this, and LCO, which is this. So I'll add them. The total inductance that I'm having is 0.25 nanohenry, right? So I'll define here 0.25 nanohenry, right? And then I'll define a line which is going from top to bottom, right? And then I have C and L, right? This C is my total capacitance CT, and this L, no. Basically, when I'm transforming this LC, this is CJ0, this is L, which is point, according to this, is 0.45 nanohenry, this is 0.45 nanohenry, followed by my 0.06 picofarad. That I am converting to series LC. So there is a transformation here. Accordingly, my L and C values are going to change here, right? And my parasitic capacitance, whatever I'm having here, is 90 femtofarads. So that 90 femtofarads I'll add up to the converted capacitance, right? And for time being, because I'm not making that conversion, I'll define here some capacitance boundary conditions. Here, because I'm having a parallel LC, I'm selecting parallel, then I'll take these two values. I'll put this as 0.5 nanohenry. I'm not putting the converted values. I'm just putting the values that I'm having right now, right? 0.45 nanohenry, and let me put this as 0.0 or the total capacitance 0.15 picofarad, right? And then I'll define the line. Once again, the direction should be same, and this is how I'll define my diode with complete package, right? And if it is on condition, then accordingly what I'll be having here is, for on condition, what I have is, I have L, I have C, here I have L, and here I have R, and here L. Once again, I'll combine these two into a single inductance. So I have L, I'm having C, and here this, whatever L and C I'm having in series, I'll once again convert them to parallel, right? So this is R, this is L, right? So here I'll convert this as L, R, and then we have the equivalent circuit, right? So this is for on condition. This will be for on condition, right? So what I'll have here is that this inductance will not change. So whatever L I have defined, that will remain same, but whatever I have defined for parallel LC now becomes parallel RLC, right? Right? This will be the equivalent circuit that I have in case, but the values will change depending on the transformation that I'm doing from series to parallel. The values of my L, C, and R will not be same as whatever I'm having in my diode case, right? So those values change, but for simplicity, I've kept the values that I'm having here, right? So this is how I'll define my diode with my parasitics. And if I'm not concerned much about my parasitics, then what I'll do is I'll select my diode, and if I'm assuming it is in off condition, I'll go say RLC boundary condition, this is capacitance and this capacitance is 0.5 picofarad. I'll select this, and then I'll put the arrow from top to bottom, right? And then I'll select my other diode. Here also I'm considering the diode to be in off condition. I'll select this 0.15 picofarad. I'll define the line from top to bottom, right? And similarly, I'll define my capacitors here. Excitation, sorry, boundary, RLC, capacitor 0.15 picofarad, and same thing here. right? So now I have defined the conditions for my diodes here. All the diodes are in off condition, right? Now let me just so this is the uh, boundary conditions that I'm going to assign when all the diodes are in off condition, right? And then to complete this, we need to define the port. So port is along XZ direction. I'll choose the plane as XZ. Then I'll choose the rectangle. Then I'll draw the rectangle. And then I'll say this is port. Okay. And then I'll define this as my X dimension is my 2.5 times speed W, and this is situated at minus sub y divided by 2, and I'm starting at 0, and sorry, my this thing is 5 into speed W, and height is 10 times. Okay, so I have defined my port here, or sheet for the port. Then I'll say right click and then excitation port wave port, right? The reason I have defined wave port is that I want the exact impedance of this line. When I define my lumped port, it considers that the impedance of the line is 50 ohms directly. When I'm defining my wave port, then it will calculate the impedance of the line. So I have defined my ports. So, and then if I want the radiation pattern to be measured, then I'll define far field, right? So now, and after that, I'll define my analysis, add, right click on analysis, add solution setup, advanced, and my highest frequency is 3.6 gigahertz. Let me put this as 4, number of solutions as 20, and then say OK. And I'm seeing this from say 1.5 gigahertz to 4 gigahertz, and step size 0.1 gigahertz. I'll do the validation check and then say analyze all. Any queries till now?
So why we are placing this lines which has been nearer to the diode sections? Huh?
Which lines? You mean to say this line? You're talking about these two lines?
Why we need this padding section as well as the other lines what we are taking outside the
Regarding them, these
yeah
lines are
yes
these lines. You are talking
yes
about these slots, right?
yes both I have doubt.
Huh. So these slots are used for segregating your biases, right? So
Okay
when
sir.
you apply your bias, you need to apply one terminal to the positive, other terminal to negative, right?
Okay.
So if you are not making these slots, the entire ground plane is a single conductor. You cannot apply, or even if you are applying your positive and negative terminals to a single conductor, it becomes short circuit. So your current will not flow through the diode. So in order that your current flows through the diode, you are making these slots and separating your negative and positive terminals of your diode so that you can apply your bias. And regarding
So
this, yeah, please,
when how do you connect these
how to connect?
to the diodes? Huh?
I did not get your query.
So we'll be connecting the diodes positive and negative now. So, but when we are using these slots, how it is being differentiated?
So if you are seeing here, we have, sorry, we have your diodes here.
Is
Where is this?
okay.
You have your diodes here,
Okay.
all 5 diodes placed here,
Mm.
right? And you are connecting the positive terminal of the, this is the positive terminal and this is the ground, right? And here you are connecting one more wire which is positive, and for that ground is same, and you are connecting positive here, positive here, and positive here. For all these, ground is same, but your positive terminal is different so that you can control the diodes separately.
Okay. Okay.
If you are not making the slots, only make the horizontal slot, all the diodes will be either switched on or all the diodes will be either switched off. But if you want the biases to be applied separately, then you need to separate the positive terminals of each of the battery. That's the reason we are making these slots. And if you see, the diode dimension is much smaller than the slot that we have cut,
Mm.
right? If you are,
Again,
if you want to solder the diode to the
we need
positive
that
and
extra
negative
paddings.
buffers, you require those pads.
Okay, sir. Thank you, sir.
So we are done with the simulation. So what does it say? It has converged. So now we'll right click, say rectangular plot, and we'll plot S11. So we are getting the return loss around 3.1 gigahertz, I think. No, 3.05, right? So you are getting somewhere around 3.05 gigahertz, and return loss is about 11 dB, right? Now this is the case wherein we have considered all diodes to be in off condition. So let me do one thing. I'll copy this, paste it, and I'll rename this as all diodes on underscore on state. Right? So what is the modification that I'll be making here? I'll go to my diodes, right? So whatever diodes I have defined here, I'll go here. I'll put this as resistance 0.42, right? Remove this. Instead of capacitor, I'll put this as 0.42 ohms. I'm only changing the boundary condition. I'm not changing the structure. 0.42. So now I have changed all my diodes to on condition, and I'm resimulating this once again.
Sir, a small doubt, sir.
Yeah, please.
Actually, we are using one positive, one negative, but there are so many wires are there. What is the purpose of that, sir?
If you are seeing here,
And also where it should be soldered, sir, at the slot portion or at the plate portion.
obviously it would be on the copper, right? Your slot is not going to take your DC current. Only your copper takes your DC current. So whatever soldering that we are doing here, if you see properly, this slot, the horizontal slot, whatever we are having here. Let me show this. What this horizontal slot is separating your DC from positive and negative terminals. So bottom side is completely negative. You are putting positive here. You are putting your positive here, right? One wire for this, second wire for this. You are having third wire here, fourth wire here, fifth wire here, and negative sixth wire here. So 1, 2, 3, 4, and 5 are the positive terminals. So you are independently controlling diode 1 using 3, diode 2 and 4 with 2 and 1, and diode 3 with 4, and diode 5 with 5. 6 is your ground. So that's what you are seeing here, right? So you are connecting the brown wire, whatever you are seeing here, this one is the ground, this one is 1, this is 2, and whatever wire yellow is there 3, green is 4, and blue is 5, right? So this is 6, brown one is 6.
Thank you, sir. Understood.
So our simulation is done. Let us see the resonant frequency. So what we are seeing here is that in all on condition, your patch is resonating and you are getting resonance at 3.68, right? So if you see, this is the case when all diodes are in off condition, right? Case 1, when all diodes are in off condition. Case 2, all diodes in on condition, and randomly you can pick these things, copy, I'll say paste. Now I'll randomly put some diodes on and some diodes off, right? So here I'll put this as off. Let me put this off. And then this is off, right? So central one is off, this one is off, this is on, this is on, this is on, right? And I'm simulating this. So now the resonant frequency is different. So it's coming around 2.53, right? So we are having different states. This is at 3.05, 3.68, and the third one is at 2.53. So accordingly, depending on the diodes you are switching on and switching off, your resonant frequency is going to change. And if you want to see the radiation pattern, then you need to right click, set up your infinite sphere. So this I'll put it as 0, and this is 360. Here I'll put this as minus 180 to 180, and then I'll run the simulation once again. And when I'm plotting, I'll plot the far fields. I'll plot the far fields, rectangular or 3D, whatever you want, you can plot and see the radiation pattern as well. So you are having any queries? I would be happy to answer them.
Sir, while doing the radiation pattern,
Hmm.
we are selecting pi as 0 to 360. Theta as minus 180 to plus 180. Why is that?
Sorry?
Sir, actually, while doing the radiation pattern, while setting the far field,
Hmm.
we are taking the pi, that is azimuthal angle, from 0 to 360 degree. And the elevation theta is from minus 180 to plus 180.
Either way, you are covering the complete 360 degrees. Whether you are putting minus 180 to plus 180, 0 to 360, either way, you are taking the complete phi change of 2 pi radians and theta change of 2 pi radians.
Okay, so shall we put
So
it like
it
0
shouldn't
to
matter.
360?
I don't think it's going to matter much. Yeah, you can put 0 to 360 as well.
Okay, sir. Thank you, sir.
Hello, sir.
Yeah.
Sir, can you show how to analyze this magnitude and phase during on and off condition?
Magnitude and
Phase angle.
phase angle.
Yeah, variation in magnitude and phase with on and off case.
So when you are looking at your first thing that you need to know is which elements are being excited, right? So if you are looking at, you want to see the current density, right? So right click on the patch and then you say plot fields. You want to see surface current density, then you go to G, right? You are having magnitude of the surface current density, vector of your surface current density, right? So let me select this, and then I'll say here in this case, because I have used interpolating, I'm getting only last adaptive. But if you are using your sweep has fast or discrete, then you can select sweep here and see the frequency at which your antenna is working, or you are getting the resonant frequency, right? So because I haven't done fast or discrete, I'm getting only last adaptive, which is at 4 gigahertz, right? So once you plot this, you will get the current distribution on this, right? And you want to see how this current distribution is varying. Then go to your fields and then say right click and then say animate. So it's varying the phase from 0 to 180 degrees in steps of 17 degrees, right? And then say animate. So it will show how the current distribution is changing from 0 to 180 degree. And similarly, you can do it for your slot as well. Right? Close this. In this case, I'll select my ground plane. Or I can also do, if I want to see the slot, then I need to select the substrate. So here I am selecting the ground plane, J surface, magnitude, and then I'll plot, right? So whatever we are seeing here is the surface current that you are having on the ground plane. and if you animate this, you will be able to see how the surface current is varying on the ground plane with respect to the phase of the signal, right? So if you want to see this for your substrate, then you are not going to have your surface current, you will be having your volume currents. So accordingly, you will be selecting the volume current density for the substrate and see the magnitude that you are getting here. So blue implies 0 and the the color is going to tell you the intensity of the surface current. Do you have any more queries?
So I have one more question, Salika.
Yeah, please.
So we were just designing a simple FSS structure, that simple slot,
Okay.
square slot FSS. So if I want to put a pin diode within that, where should I put it? Any place on that slot I can do it, sir?
Ma'am, the thing is that whenever you are designing a slot,
Yeah.
the way it works is similar to that of your dipole. So the
Okay.
frequency at which it resonates, so suppose you are considering a dipole, right? So it
Okay.
resonates at lambda by 2 distance, right? So
Yes.
whatever
Yes.
frequency you are going to get is at lambda by 2. Same is the case with your slot because it's dual of
Okay.
your dipole. So the length of the slot is going to tell you at what frequency your slot is going to resonate.
Okay.
Right. So depending on your application, you can either shorten the slot or increase its length. So
Open
basically,
it.
yeah, depending on whether you are short circuiting the pin diode or open circuiting it. So that's what we have done in this particular example, where the total length of the slot is 36 mm when the
Okay.
outer diodes are short circuited, or on condition, the total length that we are getting is 32 mm only. So the frequency will increase. The slot resonant frequency is going to increase. When the outer two diodes are shorted, like all four diodes except the central diode, all other four diodes are short circuited, then in that case, the length decreases to 13.95, I think. Or let us consider it as 14 mm. So the total length would be 28 mm. So the frequency is further going to increase. And if you are short circuiting the central diode, then the slot itself is not getting excited, right?
Yes.
So in that case, only your patch is resonating. So that way, depending on the characteristics that you are looking or the frequency change that you are looking for your FSS, you can put your diode at various positions on the slot.
So I just have a doubt, one more, sir. Like for that FSS, I have not chosen a ground plane. I just place the basic loop or slot one.
Hmm.
So only on the top of the dielectric we have a slot. That
Okay.
square slot, the basic one which I normally we started with. So if
Ma'am,
I put this,
the way we simulate your FSS and the way we simulate antennas is slightly different.
yeah, I
Uh,
can understand,
for,
sir. Like
yeah, for
that we
FSS,
have
we
taken
go
lesson
for array simulation.
unit
Generally, we
unit
go for
cell
array simulation. Yeah.
unit cell simulation we have done, sir.
Yeah, unit cell simulation with your flow ports and
Yeah.
periodic boundary conditions, master and slave.
Yes.
And then
Now,
you are going to get the characteristics. Yeah.
yes, sir. I just kept this diode on one position, and I have not used any the wire connections, that slot connection wherever you want to get for biasing. Will that affect the performance?
In simulations, it will not,
Yeah.
but
Yes, sir.
if you want to do it practically, then it's going to affect.
So we have
Because
to give an
whenever
option
whenever
also
you are
for this.
simulating in HFSS, basically you are not considering the biasing wires and other things.
Yes,
Even
sir.
when you do whatever patch we have designed with diodes, once you put your wires, the radiation pattern gets distorted. So we need to isolate your DC wires with your antenna. So that's the reason we put the biasing T, which isolates your RF and DC. But there, your RF is not going to DC, but your wires, whatever are there, which are hanging, that will affect the radiation pattern of your antenna practically. In simulations, you will not see any effect, because you haven't included those wires in the simulation. So when you are doing it for your FSS, you may have to consider the wires. If you are aligning those wires along with the coppers, then it may not affect much. But if they are crossing over with the slots that you have made for FSS, then your characteristics of FSS are going to change practically.
Okay,
In
sir.
simulation, you may not see any effect.
Sir, shall I send you my results tomorrow such that will you be just make it clarify whether we are done is correct or not?
Yeah, you can send it, but I may take 1 or 2 days because
Sure.
tomorrow we are having a lab exam.
Okay.
So maybe I may not be able to reply immediately tomorrow. I'll
Okay.
be taking 1 or 2 days.
Okay, sir. Thank you, sir. I'm Dr. Sapna from Kalina Karnanadi Institute of Technology, sir. I'll just send it tomorrow.
Sure, sure.
Thank you. Thank you, sir.
Thank you.
Sir, one doubt.
Yes, ma'am.
Participant has asked, if a patch is designed for 4 gigahertz and a slot is introduced, slot is resonate at 2 gigahertz, where the final one will resonate.
Patch is designed for 4 gigahertz, okay, and a slot is
Slot
introduced. Slot is resonating
slot
at 2
is
gigahertz.
resonating at 2 gigahertz.
Where the final one will resonate. Basically, depending on what is the loading that you are going to have because of the slot, the final resonant frequency might not be exactly at 4 gigahertz, depending on the loading that you are having from the slot. And depending on whether you are going for a reconfigurable antenna or not, if you are only using a patch and a slot, then your slot might be resonating close to 2 gigahertz, your patch might be resonating close to gigahertz. So you may get dual band. But if you are going for a reconfigurable one, depending on the length of the slot and the loading that you are going to have by patch and the slot, either ways, the frequency may not be exactly at what you have designed. There, because of the loading effect, the frequency will be slightly shifting.
Okay, sir. Thank you. Thank you very much.